Okay, so today's session is on vision transformers, or you often see it as called a ViT, V-I-T. But in order to understand that, I think I want to first give a brief introduction about the vision model, the deep models in vision generally. So I have made up not made up, but I have organized a timeline, and it shows that in each year, what are the major breakthroughs in deep models for vision. So the first one is the LENet. I think it's taken from the Yan Nakun, who is the author of this. And basically he proposes the basic convolutional neural network for handwritten digit classification. So he proposed the kind of the backbone of the convolutional nets, the structure of it, right? So like you take different convolution layer, you take mask pooling, and then you concatenate together, and then you got your final output. But in the beginning, it's only a 5 hidden layers, so it's not that deep. It's just that back then it's not possible to train. There are so many issues with like training a really deep network. So at that time, so he proposed like a 5-layer convolutional nets, and it can solve the handwritten written digits pretty well. So that's like 1998. And then, so you see there's a gap. I think the gap is for people to develop a better training algorithms, like this, all this like optimization algorithms, and also the development of GPUs, which makes a massive training possible. The other is like people start building the data sets. So that's when, like around 2010, large-scale image datasets become available. So the ImageNet was born in 2009 from Stanford, and also this VOC dataset, another dataset for object detection, is also proposed at that time. So this becomes the benchmark datasets for different researchers to post their performance. So people can say, so it makes a kind of makes a standard to evaluate whether that vision model is good or not. And then in 2012, the first deep CNN is proposed. It's called the AlexNet. I believe Alex is the first name of the author. So it's the first deep CNN is proposed and applied with the GPU training in 2012. And then in 2014, then the variety of large, deep convolutional neural network is proposed, and like such as the VGG is a very famous first version of the large models. Convolutional nets, and also RCNN, and also the inception concept by also call it a Google Net, is also proposed as in that time. And then in 2015, we comes the faster version, and also another very famous architecture called Residual Network is proposed in that time. So the Residual Network is basically like the basic building block of the residual network is to skip the blocks, the skip layers, right? So you can directly transfer the X into directly to the output to solve the gradient decay problem that people observe when training a really deep network. So ResNet is still kind of the, I would say the benchmark to beat in computer vision. And that's why, like when you see the Stanford seminar, you will see that the author actually prepares the transformer, vision transformer to ResNet a lot. And then data from 2016, again, people start develop like even larger model, right? So you see the inception from 2014 and to 16, that becomes inception V4 already. And also people start to propose faster ways to do image object recognition, mainly for auto driving, such as like a YOLO model. So this is like a what is YOLO model looks like. So YOLO stands for you only look once. So it really aims for the speed of object recognition. So basically, the basic idea is you kind of create many grids, right? So you create many of these patches of the images, and then you quickly estimate the classification, like kind of the class labels for each of the batch, and then based on this information, you can just extract like further refine the bounding box around the object. So that's a basic idea. And then the YOLO model has been developed till, I believe right now, maybe even V4 or V5, or maybe V6, I don't know. So there's like many iterations of this model that focus on speed of like object detection in the streaming, in the image, for example, in the video, right? So it's using this model. And then in 2017, Transformer is born. Transformer was originally for mainly proposed for sequence model, right? It's like the languages. So that's where like when people start using Transformer, they mainly like report its performance on language task, such as machine translation or the text classification, etc. And then the next year of the Transformer, BERT is born. So the BERT, although BERT mainly use the encoder of the Transformer, but it also proposed a very important concept of pre-training and fine-tuning afterwards. So it proposed a concept of like first pre-training a really large data set, and then adapt that pre-trained model to following or downstream task, or adapt that large model to the downstream domains, which I will also talk about how to do that in vision. And then in 2020, then image related, and of course, like after all this period, people start to develop like faster versions, like Inception, different versions of that, and also YOLO model also gets improved during these years. And then in 2022, people think that we can use the same, basically the same GPT model for images, right? So we can use the generative model, just like ChatGPT, that we can use the same model for language generation. We can also use it for image generation. That's around 20. And then in 2021, that's when like a vision transformer is born. I think it's also proposed by Google. So it's really interesting that Google, like this, the major, many of these major breakthroughs, including Transformer and BERT, is actually proposed by Google, including the vision transformer. Yeah, so in 2021, that's ViT is born. And then afterwards, there's like also many different iterations of ViT to make it more efficient and also able to make it like able to train on a large scale of images. Okay, so moving on next. So you see this timeline, right? And then we can look at we can look at the model size, which is like how many operations in the model, and then the accuracy, right? So you can compare in terms of like as the model get larger and larger, how the accuracy kind of evolve with that. So you can see that, for example, in the beginning, which is the LENet, I believe LENet is not here. The AlexNet is here, right? So the AlexNet is down here, although it's large, but but it has it's like really low performance over here. And then I think like when you move on, like a VGG model is also very large, and actually it is the state of the art at that time, but it is not the kind of the still the state of art here now, right? So it's the performance is beaten by the Inception model, which the Inception model was always although it's like a medium size, but it can achieve like the best performance in terms of the top one accuracy of the classification. Basically, you take the maximum score of all the classes and treat that as your result. And yeah, and the result is reported on ImageNet most of the time. Okay, and the next we can talk about the visual task adaptation benchmark. So as you can see right now, right? So we have like we can train like a really large model, especially like after that, especially for transformer, right? So you can train really large model, and then how can we train a large model and further adapt to the following task? So over here, so this shows like the main flows of pre-training and also transfer the knowledge for the downstream tasks. So what does it mean like pre-training? So pre-training is basically like you train the model on a really large data sets in the beginning, right? And then you are going to basically you learn a representation distribution of the inputs, say the input is images. And then once you train on a large data set, such as the ImageNet, right? And then later on, you have your own data sets. So you have your own task, say, to do the classification, and then you can adapt the model. So there will be adaptation algorithm, or we also call it like a fine tuning, like you fine tune the model to adapt it to your own task. So you are going to train directly on these training sets, right? So for various different tasks, say this is still kind of like a cat or dog classification, or this is more difficult, challenging, like this plain landscape classification or the game scene classification. So you can transfer it like to the downstream task, and then you can also report the performance on the test data sets. Basically, in the transfer or downstream learning, you adapt this representation distribution that you learned in this space. So that's a basic idea of pre-training and transferring, and actually lots of I would say lots of ideas has been formed around the pre-training, because like pre-training is very critical. To improve the efficiency of the model and also make it directly leveraged by different tasks. So how do we do pre-training? Actually, this material is also derived from the Stanford course that they have listed out like a different ways of to do pre-training. So the first is like a self-supervised. So what is like a self-supervised? The self-supervised means that the labels are automatically created without manual efforts. So basically, all of these labels you can directly create them from the data sets. For example, so how can you do that, right? So for example, you can do a rotation task. Basically, you just produce like 4 copies of single images, and then you rotate it by like different degrees, and then you let a network predict what is the degree of the rotated image. So basically, you create a classification task automatically. So it's a 4-class classification task. So I hope that you understand like what is a self-supervised right now, right? Because it's like the labels can be automatically generated in that process. Or similar, right? So you can have like some other operations, and then you can train a model just to predict the long transformation of the images, or even to predict the spatial relationships of the different image patches, so that you hope that the model can understand the image content, and then understand what's the relationship of the patches, like the jigsaw or the relative patch location. Basically, it takes the relative location of 2 given patches and to predict whether the second patch is at the bottom or at the top of the first patch. Yeah. So in the literature, people has been discussed like what is the this like a self-supervised trained classification performance versus the downstream accuracy, right? So you can we hope that it's like a linear line, right? The more better you can get at this pre-trained self-supervised task, the better it will be in the downstream accuracy. We hope that's the case, but sometimes there can be some outliers there, yeah. For example, the widest VGG model, the yellow ones, is the best for the rotation, right? So in terms of rotation, it has the best performance over here, these dots, but it has the lowest performance in terms of the downstream ImageNet prediction. Yeah, so that's on the self-supervised pre-training. And then moving on, the author also proposed another way, like it's called a semi-supervised pre-training. Semi-supervised means that basically it's like in these data sets. So you have a pool of images. Well, some images you don't have labels, right? So you don't have any labels. And then there is the small set of images where you have the labeled images. So you want to do some self-supervision with the images that don't have any labels, but at the same time, you want to do some supervision for these labeled images. So that's why it's called semi-supervised. Right? It's like partly unsupervised, partly supervised. So what the idea here is that you can still do the self-supervision task, which is to predict the rotation degree of the images, right? But you can also leverage the labeled images. The labels, for example, it is the head. Like even if it's rotated, it is still a head there. So basically the model is doing two tasks at the same time. Like one task is to predict the rotation degree in the self-supervision. And the other is like to predict the exact class labels of the images. Yeah, so I think it's pretty straightforward to understand like semi-supervised, like where you can also leverage the partially labeled datasets really well. So I have seen a question in the chat. So about any pre-trained models that combine computer vision and NLP, which can be used for document classification. Yeah, I think it's a very interesting question. And actually, yes. So it's called a multimodal. So to your question, like a pre-trained model that's combined vision and text, is called a multimodal model. Especially for transformer, because the transformer right now kind of can take in the text and images like very naturally, right? So people have been developing a really large model that can process text and images at the same time. So if you are interested, you can search for multimodal. So transformer. Is that a simple feed-forward network than using the layer? Oh, you mean this? This, yes. So usually like on top of the large model. So usually like on top of this, say, no matter like a convolution network you are using or like a transformer you are using, like on top of that, if it's a classification task, you can just do a feed-forward network. And then you predict the classification basically on the and predict the classification head. So you basically map the output from the large models to the class labels. Yeah. Okay, let's move on. And then over here, so it shows that the performance of the semi-supervised model. So they call it MOAM, and it reports like a very good performance by just using ImageNet like 10% labels, like without using like 100% of labels. It just train with 10% of the labels in ImageNet, and observe like a state of the art on the top 5 classification problem or top 1 classification problem. Okay, next, so we have talked about self-supervised, semi-supervised, and then it comes to the big transfer, which is the fully supervised pre-training. So I guess you already can guess like what is fully supervised, right? Basically, you just like the whole data set, you fully the whole data set is fully labeled, and then you just like do a fully supervised pre-training with all of the labels. And these models mainly use the ResNet over there. So, and this is like in a Stanford lecture. It points out that you need to be really patient because it can takes long to pre-train the model. For example, if you see the model pre-train like on 8 weeks, it's nearly flat. But if you kind of like 8 GPU months, of course, it doesn't mean that you trained for 8 months, but it's like 8 GPU months. You can see that there's like a gradually like increasing of the performance over there. So be patient. The pre-training usually can take long. But once the model is pre-trained, the authors or publishers usually just make it public, make it shareable, so that any following users can directly load in this pre-trained model and then fine-tune it on the following task. And then it has been also discovered that the model size is important, and at the same time the image size is also important. So basically the how large your pre-trained data sets is also important. For example, over here, so these dots, the size of the dots represents the size of the model. So yeah, so if it's like and you see that the largest one is the blue one. So blue one is the largest ResNet over here. So 152 means like 152 layers. And 4 means like you like basically the width of the hidden layer. So basically you multiply them together, that indicates the size of that ResNet. As you can see that if the model is small, right? So if the model is small, and if the pre-trained data sets size increases, you see that the model actually capped with more labels. Actually, the model, the small model won't improve afterward. However, for the large model, right? So these blue and orange ones, with more images for pre-training, the performance will improve. So it actually tells that both the like how large data sets you can use for pre-training and the model size are both important. So you need to scale up everything, both the model and images, in order to reach the result, reach a better performance. Yeah. Thank you for answering some of the questions. And then later on, I think and here it also shows that, right? So here is like a different model size, and then this is the accuracy, and then you can tell. I think the green one is the model is like the model is trained on a smaller data set, and the blue one is a medium-sized data set, and orange one is like a really large pre-trained data set. So you can see that, yeah. So how like this is the largest model, right? So largest model trained on the largest data sets outperform all. And it reports the performance on this. This is like a one image benchmark, like for one example classification, and then this is another benchmark, or the same benchmark, but it's like 4 or 5 example classification. Yeah, I think what we learned from all of this is that actually before transformer, or actually before the vision transformer, there has been a lot of development in terms of how to pre-train the models, right? And even when transformer comes into place, people still applying kind of similar techniques there. to see like, okay, how can I pre-train the transformer on a really large data sets, and then it will show the performance. And that will also lead to recent ChatGPT. Well, the ChatGPT is like hundreds billions of parameters or more, even more. It will it can has like really, but it again will train on a really large data sets over there, right? So that's why it can gain the performance. You will see like a big performance gain when they scale up everything in terms of both the model size and the pre-trained data sets. Okay, then let's move on to so okay, then let's move on to the vision transformer. So when so why do we need vision transformers? First, well, what's the advantages of using a vision transformers? So first, not all pixels are equally important, right? Because in the convolution just apply the same filters over all pixels in the images regarding like each pixel location with some skips, right? But it applies the same filters all over the place. I want to just show an example over here. So in a convolution operation, basically you just do like a filter. So you can think of these weights as a filter that is trying to capture some features of the images. And then it will kind of roll through the pixels, right? And then the filter weights won't get changed. The filter weights are kind of static. So at each convolution operation, at each pixel location, it's going to kind of scrolling across all the positions with the filter weights remain the same. So that's the convolution. But if you compare it to the attention is quite flexible, and I would think of attention as a contextual weights. Contextual weights that the weights will differ every time based on its input, based on its position, because like different positions may have a different if important information, right? So you will see that when you're scrolling across the pixels, you will see that these weights will be different based on its locations. So moving on to the next position, the weights will change based on the context. I hope that this kind of help you understand the difference between the convolution and attention. The main difference is the convolution filters weights are fixed across different locations, while the attention weights will be dynamic and contextual at different locations. And next, yeah, so with the attention calculation, it brings the benefits of not the concepts are not like not all concepts are shared across images, because convolution you kind of apply the same concept, the same feature detector at each location, right? But with attention, you kind of more dynamic, because at different locations of the images, you may get a different feature filters based on the attention mechanism. Another challenge is like convolution struggles to relate spatially distant concepts, because the convolution operation is quite like a local, right? So because and in order to get the distance relationship, you need to do multiple layers of a convolution for you to reach like the pixel like in a distance. But with the attention, actually like just in the transformer itself, I think the transformer is originally proposed for the languages, so that it can refer to the word far away in a long paragraph. The same applies to images. Like if you use the transformer, you can attend to the pixels or image in patches like far away. So another question is on the masking has to be part of some labeled set. Yeah, depends on the task, right? So self-view, like in the beginning, in the self-supervision task, we just define the rotation is a full class classification, right? So we just predict like one label there. The same for image classification. You just need to predict whether that image is a cat or a dog. You don't need to you don't need to kind of classify all the foregrounds of that object. And I think if you mention like the foreground, then usually it means the mask, and it calls like it's not a classification problem. Then it's an object detection problem where you need to for example, I think it's in like in being over here, right? So for example, this this figure, like this dog, you need to create a box around the dog, and that will becomes your foreground. The self-supervised right now, yeah, people when they do the self-supervision with these operations, it doesn't involve any foreground. It's just a simple classification task to predict the degrees of the images or predict the relative location, like top, bottom, left, right relationship of the image patches. Okay, and then moving on to the vision transformer structure. And I think to really understand the transformer, I hope you to look at the step-by-step into transformer, my previous blog. I think it's quite intuitive to understand like this transformer structure. So let's just like assume right now that we use a transformer encoder. Well, it's going to take a sequence of inputs, and then it will put out a head for classification. And then you can train some on top of that, like a multi-layer perceptron to map this head to like a multiple classes. So over here, so how can we convert the images into kind of a sequence type of model? So over here, you can see that like for example, you can split the images like into several patches. For example, here you just split the images into 9 image patches, and then you put them into a sequence. And then you do a linear projection. So this is like you can learn, right? So you can do just you can treat each image as a word, just like the word in a sentence or in a paragraph, right? So right now the word is like the images, and then you're trying to learn the representations for all of these like images. And on top of here, like similar to text, you will get like an embedding to learn about the content of the images. You will also get a positional embedding that encodes the position of that patches in the original image frame. And then you pass it through transformers. The following step is exactly the same. It's exactly the same with like a language transformers. And over here, it shows like what is a transformer encoder looks like, right? So you have the embedded patches, and then you pass it through a normalization, and then you have this multi-headed attention. So in terms of like a multi-headed attention, you can again read through this step by step into transformer. You will see like you will see what it like looks like. So let me put a link over here as well. So if you want to kind of get an understanding of what is transformer, you can look at this link. You can also look at like previous recordings on the introduction to transformer. But I want to make a point that actually like to apply transformer to images is quite straightforward, right? So you just need to create the image patches and then treat these image patches as word. Okay, and then over here, the regional author have proposed like a different models of different sizes, right? So we call it like a ViT base model, ViT large model, or huge models, and it has like this many different layers and hidden sizes. Like huge models has 32 layers, and this much larger hidden size, and this is like a total number of parameters. Well, actually to current standpoint of view, this many parameter is no longer huge anymore, because I think right now we train like even much larger than that. But let's see like how the model size kind of influence the model performance. That's correct. All of these are deep neural network models. But I want to point out, because the deep neural network models has different architecture, right? So convolutional neural network is one architecture, transformer is one architecture, and there are also so many variants of convolutional nets and transformer. So this all belongs to deep neural network. It's just the architecture is different. The configurations of the network is different in terms of how big or small are these models. Yeah. So this is like a ViT BLH. And then I will first show you the results first. So you will see like, so this is like ViT 32 batches, 16 batches. And actually 32 means the patch size. So 32 means like 32 pixels by 32 pixels. And 16 like is 16 by 16. Right, so actually, the larger the image patch, the smaller the model, because the sequence will be shorter with the larger image patch. So this image, so right now over here, the dot size indicates the size of the model, right? So and the ViT over here is using the ResNet. So basically, it's using the big transfer that I have talked about previously, using fully utilizing the supervised label in the pre-training. And you see that the and again on the x-axis is different pre-training data sets from a smaller size to a larger size. So you can see that with this vision transformer, if you pre-train it with a smaller set, actually the performance doesn't beat the traditional residual network. However, if you like comparing to the gray ones. So however, if you kind of increase the pre-training size for these models, you will see that it's on par performance. But if you pre-train the transformer, vision transformer with the really large data sets, it will start to kind of beat the convolutional nets. So like in order for this vision, the transformer to work, you need to put like to large model, and also you need to pre-train it on a large data sets, like to beat the residual network. Yeah. And over here it also shows like different. So this is like a number of pre-training samples. Again, it's based on like how many samples you use to pre-train, and comparing the ViT, the vision transformer, versus the BiT, which is using the residual network, right? So like when you pre-train with more and more pre-training samples, the ViT is going to outperform the convolutional network. Although here the example is still doesn't show like improved by that a lot, right? But like as you further down increase the size and also increase the model size, and also like for example using the GPT model right now, you will see that the performance will outperform comparing to traditional models. Okay. And next chart is also very interesting. It's showing some like limits like it's showing that like how much more we can improve based on this model size or based on this pre-trained data size. So here is this is showing the compute. So it's like the more compute you will use, usually the better the performance. Basically, you pre-trained like a longer period of time, it will have you will have like a better performance over there. And Y here shows the ImageNet error rate. So the smaller the better. It shows the performance of the classification, right? And then I think the blue ones. So the blue ones is a smaller. It's a smaller model, right? So the blue one is a smaller model, and the red ones are large models. So you will see that like from smaller models to these large models, actually there is like an exponential limit frontier for the classification performance over there. Right, so you can see that, and actually there will be some trade like off the frontier. Right, so you see that if you pre-train a model that is on a small data set, for example, the dot is small, so the small that is the pre-trained data size is small, and then actually the more you trained, it will fall off this frontier. So to enable to kind of get to this frontier, you need to have like a right model corresponds to a right image pre-trained image set. And then the same is here, like the performance on the image 10-shot error rate, right? And also since it's exponential, it means that actually to further improve the model performance, it would require much more computing resources to further reap additional 1%. So it will become more and more challenging. And I guess that's why usually like in recent papers, if you see there's a improvement of like 1% or 2%, it's already like a huge improvement, just because of this, we are reaching this frontier of the performance.